Hi guys, today we're going to be continuing our study of exponential functions. This is the last part of chapter 6, and we're going to be looking at how to invert exponential functions in particular. Now there are a couple of things here which are assumed. First assumption is that you already know the basics of how to invert a function, right? We saw that in chapter 1. If you're not sure about that, you need to go back and review. The second thing we assume is that you know what the graph of an exponential looks like, and also what the graph of the natural log looks like. So in other words, if you're not sure what the graph e to the x looks like, or you're not sure what the graph ln x looks like, then you need to go back and to check that, okay? But we're going to continue now. We're going to start with our first question. We want to find the inverse function of e to the x plus 2 for a domain where x is all of the real numbers. Now, with all of the other inverse functions, the first thing that we did is we tried to sketch out what this particular function here looks like, what the original function looks like. And what you should see is that this graph is going to be the function of e to the x, right? So it's going to be this thing, but plus 2. So what does that represent? That represents a shift up by 2. If you're not entirely convinced of that, let's just take that graph there. We've got y is equal to e to the x plus 2. We could rearrange that a little bit. Y minus 2 is equal to e to the x. So this is going to be like the graph y equals e to the x, but we've replaced y with y minus 2. So that's a shift up by 2 using the rules that I gave you earlier. Or if you prefer, if you just want to think about it simply, you've taken this graph here and you've just added 2 to it. So everything shifts up by 2. So what's this graph going to look like? Let's draw it out. Draw my axes here. Ooh, that's not very good, is it? Again, a bit better. There we go. Okay. 1, 2, 3. Now we know that the graph of e to the x is going to look like this. It's sort of like that, right? It passes through the point where y is 1, so it's got a y-intercept of 1. It grows exponentially on the right-hand side, and on the left-hand side, it gets smaller and smaller and smaller and approaches the x-axis, right? It never actually touches the x-axis, but it gets closer and closer to it. Okay, so what happens if we shift this up by 2? Then we're going to get this graph here, aren't we, right? We're going to shift up by 2, which means that the y-intercept is going to become 3, and the graph is going to get closer and closer to the line y equals 2, instead of getting closer and closer to the x-axis. So we're going to have this particular graph here. Sorry about that, it's not so great. Let me try to do that a bit better. Something like that. Okay, so this here is the graph of f of x. Now, why did we bother to do that? Well, the reason is because we need the domain and range of this function in order to think about the inverse. So let's do that. So we want to get the domain and the range of our particular function here. So we've got our function f. Okay. We want to think about our inverse function f inverse. So what's the domain of this function? Well, x can be any of the real numbers, right? From negative infinity to positive infinity. So we can say that the domain is x is all of the real numbers. Now, what about the range? Well, the range has got to be everything that's greater than or greater than 2, right? Because the graph gets closer and closer and closer to 2, but never actually touches it, and it grows for all the values above. So the range is y is greater than 2. Now you should remember that this helps us to find the inverse function, right? Because the domain of our original function becomes the range of the inverse, and the range of the original function becomes the domain. So what's the domain of our inverse function? Well, if the range of the original is y is greater than 2, then the domain, the inverse, is x is greater than 2. And in the same way, the range for the inverse function is that y is all of the real numbers. So what does that lead us to expect? It leads us to expect that we should have a graph where the domain is x is greater than 2. So let's try to sketch that on here. So we expect our domain to be everything that's greater than 2. And we expect our range to be all the real numbers. So in other words, we expect a graph, right, that's going to occupy all of this space here, right? Because that's the space where x is greater than 2, and the y values can be any of the real values. Okay, so we expect our function to be there. What else do we expect? Well, we expect the inverse function to be a reflection in the line y equals x. So if we just draw that on, let's try to draw the line y equals x. Sorry, it's a bit rough. Right. Here we go, reflection in the line y equals x. And then if we know anything about the reflections, then what we should expect is we're going to get something that's going to look like that. Okay, so that's kind of our guess at the moment as to what the inverse function looks like. So the question is then, now that we've kind of got all this information, we know the domain and range of the inverse function, we've got a rough idea of what it should look like, can we actually find the function? What we're going to do then is we're going to take our original function f of x, so we're going to write here y is equal to e to the x plus 2. And remember, to find the inverse, what we're doing is we're rearranging to make x the subject. So we get y minus 2 is equal to e to the x. Converting that to the logarithmic form, we get x is equal to ln y minus 2, right? So that is the log base e of y minus 2. And if that's the case, then we know that the inverse function, f inverse x, we just replace then the y with an x, is equal to the natural log of x minus 2. Okay. Now, if you know what the natural log of x looks like, you know that the natural log of x is going to look like this. I'm just going to draw it on the graph. Look like that, something like that. Right, goes through the x axis at x is equal to 1. So what will the natural log of x minus 2 look like? Well, it's just that graph, but shifted to the right by 2. Okay, and lo and behold, that is exactly the curve that we've got there, right? That is the graph of ln x, but shifted to the right by 2. Okay, let's try another example. Let's try a slightly harder one. So we want to find the inverse function of 3e to the power of 2x minus 1. All right, same thing. Let's sketch this particular graph. We're going to sketch that graph. What does that look like? Okay. Well, let's do a little bit of rearranging, shall we? So y is equal to 3e to the 2x minus 1. So y plus 1 is equal to 3e to the 2x. And so we can divide both sides now by 3. So we get y plus 1 over 3 is equal to e to the 2x. Okay, now what I'm trying to tell you, what I've been trying to tell you for a long, long time, is this is the graph of y equals e to the x, but it has undergone some shifting, some stretching, some scaling. So let's try to figure this out. What have we done? We have replaced x with 2x. So what does that mean? That means we have squashed in the x direction by 2. And if we replace x with 2x, we've squashed in the x direction by 2. Another way you can think about that is you've scaled it, but you've scaled it by a half. It's the same thing. Secondly, we have replaced y with y plus 1. What does that mean? Well, that is a shift down by 1. Right? Because you can think about that. That is a shift in the y direction, but by -1, you're going down. Lastly, we've replaced y with y divided by 3 in effect. What does that represent? That is a scaling or a stretching in the y direction by 3. So what do I anticipate? Well, we've got the usual graph right here, that's 1, of y equals e to the x. And what are we saying has happened? We're saying that this graph has been squashed in the x direction by 2. Okay, so we're expecting that it's going to be squashed like this. So we squash, squash, squash in the x direction. We're also expecting that it will be stretched in the y direction by 3. Okay, so if it's stretched in the y direction, for example, this point here, the point y is equal to 1, well, that's going to get stretched up to 3. So we're going to have a graph now that's going to look like that. Right, it's supposed to go through 3. Really terrible sketch, but never mind. And lastly, we're expecting it to be shift down by 1. So in the end, we're expecting this graph to actually go through y is equal to 2 and come down there. Okay. Now, if you're really not sure about that, then what we're going to do is we're going to just do that on Desmos. So if you just give me a second. Okay, so hopefully what you can see now is Desmos is up. And I've got here the graph of y equals e to the x. I've also got the graph 3e to 2x minus 1, but I've hidden it. So let's just take this. If I've got y equals e to the x, if I replace x by 2x, then what happens? You can see I've squashed it in the x direction by a factor of 2. So just watch that again. There we go, squashed. Next, if I take the y and I replace it with y divided by 3, what's going to happen? I'm going to stretch this in the y direction. So there we go. You've stretched that in the y direction. Let me just get rid of that again. That. Okay, so we've stretched. And lastly, we've replaced y with y plus 1. So that's going to be a shift down by 1. Oh, beg your pardon. There you go. That is a shift down by 1. Try that again. See that? Down by 1. Again, just to double confirm that that is exactly the same as the graph that we've got here. There we go. That is exactly the same line. So to clarify, we should be able to sketch our function y equals 3e to the 2x minus 1 by just thinking about each of the separate operations, right? Namely, we have squashed in the x direction by 2, we've stretched in the y direction by 3, and we've shifted it down by 1. And that's going to give us a few key points. Most importantly, that we've got the line gets closer and closer and closer to y equals -1 down here at the bottom, and it crosses the y-axis at y is equal to 2. Okay? Now then, let's return back to our whiteboard. Okay, so we're back to our whiteboard. Let's just get rid of all of the other graphs that we don't need. So let's just get rid of that one, and that one. Okay. All right, so we know that we're going through the y-axis at y is equal to 2. We know we're getting closer and closer and closer to the line y is equal to -1. All right, well, let's use this information. Remember, what we want to do is we want to find the domain and the range of our function so that we can also find the domain and range of the inverse function. So let's do that. What's the domain of this graph? Well, domain is all of the real numbers. Okay, so domain is x is all of the real numbers. What's the range? Well, the range is everything that's greater than -1, right? Because the graph can't go below -1. So we're left with that. And if that's the case, then we can also find out the domain and range of the inverse function. The domain will be x is greater than or equal to -1. The range will be y is all of the real numbers, right? Using the same principle that I did in the previous example, the range becomes the domain becomes the range, vice versa. So what are we expecting? We are expecting that our domain is everything that's greater than -1, all of that, and the range can be all the real values, right? So in other words, we're expecting our graph to occupy all of this space. Okay. If we know what the, furthermore, if we know that our graph has got to be a reflection in the line y equals x, so let's draw that on. So that, bit rough, but never mind. That's the line y equals x. That's also going to give us an idea what the graph is going to look like. We should expect that it's going to cross the x-axis at x is equal to 2, because here the y-intercept was at y is equal to 2. And we should expect furthermore that it's going to cross the y-axis at y is equal to -1, because in this, the original function, it crosses the x-axis at x is -1. Draw this graph on. What I'm saying is we should get this thing here, something like that. Okay, that is a reflection in the line y equals x. So the question is now, can we actually find the inverse function? Well, all we got to do now is we've got to do our rearranging. So y is equal to 3e to the 2x minus 1. We need to rearrange to make x the subject. So y plus 1 is equal to 3e to the 2x. So e to the 2x is equal to y plus 1 divided by 3. We convert this into logarithmic form. 2x is equal to ln y plus 1 divided by 3. So x is equal to a half ln x plus 1 divided by 3. Okay, and so then if we just convert that to the inverse function, we're going to replace the y's with x's. We've got a half ln, right, that there is supposed to be a y, beg your pardon. Half ln x plus 1 divided by 3, right? And so this is our inverse function. We've got to ask the question, what does that look like? Well, that graph is going to look like y equals ln x, but it is going to be shifted to the left by 1. It's going to be stretched in the x direction by 3, and it's going to be scaled in the y direction by a half, right? So in other words, it's going to be squashed in the y direction by half. And you should actually notice that that is basically the opposite of what we had for the original function, right? In terms of the squashing and the scaling. So we go back to our original graph here. What I'm saying is this function here, f inverse, is equal to the half ln x plus 1 divided by 3. Go back to that. And that does make sense, right? Because if we look at this graph, we examine it really carefully, what we should see is we have got the ln graph that is shifted to the left by 1, that is scaled in the x direction by 3, and that is scaled in the y direction by a half. Okay, and probably the best thing to do to double check that is now, again, we just go to Desmos and we see that in action. Okay, so here's our Desmos. I have sketched on here the graph of y equals a half ln x plus 1 divided by 3. You should see that it basically corresponds with the sketch I gave you before. And I want to just double confirm about how we can understand this graph. So I'm going to compare it with the graph of y equals ln x, right? So let's just take that. Y equals ln x. What happens if I take that graph and I replace the x with x divided by 3? Right, I've scaled it in the x direction by 3. So look at that. Right, instead of ln x divided by 3, I've stretched it in the x direction by 3, and you can see that the x-intercept goes from 1 to 3 here, right? Now let's take x and replace it with x plus 1. What's happened there? We have shifted to the left by 1. Right, so instead of the x-intercept being at 3, the x-intercept's now at 2. Instead of the graph going towards the y-axis, it goes towards y is equal to -1. And then lastly, what's going to happen if I put the half at the beginning? Well, that's going to scale the graph in the y direction by a half. Right? It's like squashing it. So we have a look at that again. Take that graph. Okay, we've squashed it. Okay. So this is our graph of the inverse function. Let's plot it against the original function. There, that's f. How can we double check that that's right? Well, we're going to plot the line y equals x. And what do we see? We see that our inverse function is indeed a reflection in the line y equals x. Okay. Now, as you probably noticed, right, all of this is getting towards the more complicated end. But what I'm trying to get you to think about is the better you are understanding shifting and scaling, the much more confident you're going to be with doing all of these inverse functions correctly. So that's actually the core skill. You need to keep working at understanding how these graphs are being shifted, scaled, stretched, reflected, and all of that stuff. Second thing is I want you to really think about, again, this idea of domain and range, right? Because the more you understand that as well, the more you will be able to compute these inverses. So these skills, right, you can just think about, oh, I'm just rearranging an equation, but you're not doing that. What you're trying to do is you're trying to understand what's going on. And that is the thing that's going to take you time, and it's going to take you effort, it's going to take you practice, and it's also going to require you to be playing with these functions, right? Just keep typing them into Desmos, keep trying to get a feel for what's going on. It is something that will take you time, but in the end, if what you get is you get an understanding, then you will be confident and much more competent to do these kind of questions. And that's what we're aiming for. Okay, guys, I hope that that was helpful. I will see you again next time.